This is CBS Eye on the World. I'm John Batchelor. I welcome Dark Matter, What We Know and What We Want to Know, a new book, The Elephant in the Universe, 100 Years Search for Dark Matter. Govert Schilling is the author, and we begin 100 years before this moment. Jacobus Cornelius Kapteyn, born 1851, writes a paper in May of 1822 that is revelatory. It's entitled First Attempt at a Theory of the Arrangement and Motion of the Sidereal System. That paper has in it this sentence: the amount of dark matter from its gravitational effect. Govert, a very good evening to you. Thank you. Introduce us to Mr. Kapteyn. What was it that brought him to make that speculation that we now spend so much time puzzling over? Good evening to you.
Yeah, hello. Very nice to meet you, and thanks for having me. Jacobus Kapteyn was a Dutch astronomer, and as you said, his paper in 1922 was a groundbreaking paper because 1 century ago, astronomers hardly knew about the universe that we know of. We now have this wonderful James Webb Space Telescope that's discovering galaxies out to billions of light years away. But 100 years ago, no one was even sure whether or not our Milky Way was alone. And Kapteyn was one of the few who thought that the Milky Way galaxy was the only thing in the universe. It was later called the Kapteyn universe because he thought that was all there was to it. And he thought that other spiral galaxies, spiral nebulae as they called them back then, were actually objects in the Milky Way. So he made this whole plan of his idea about the layout of our Milky Way system, which to him was all of the universe. And when he thought about that, he realized that the gravity of all those individual stars had to be governing the stars' motions. And then you can turn this idea on its head and say, if I study the motions of the stars, I can find out about the total gravity. And if you study the motions of all the stars in the Milky Way, you may be able to find the gravity of matter that you have not been able to see. And that was a rather groundbreaking realization. And 100 years ago in this paper, he was the first one to introduce the term dark matter. So that's, as you said, it 1 century ago, and the whole mystery actually started back then.
Now we go to another Dutch astronomer, radio astronomer, Jan Oort, who's the Oort cloud. But what he got in his paper, 1932, the force exerted by the stellar system in the direction perpendicular to the galactic plane and some related problems. I love the humility here.
Yeah.
Wonderful. And what I get from Jan Oort is to picture this galaxy, our Milky Way, as a carousel, spinning and spinning and spinning. But therein lies the problem. How does it hang together? How does it not fly apart? Did Jan Oort see that there was a missing explanation?
In a rather different way, he did see it. He was actually a student of Kapteyn, so the two were very much related. And Jan Oort was a famous Dutch astronomer, worldwide fame, and he was actually one of the first to discover that the Milky Way is rotating. As you said, like this carousel, flattened disk of stars rotating on its own axis. Now, Jan Oort knew he could not do what Kapteyn suggested because you would have to study the motions of stars throughout the Milky Way. And that was beyond the possibilities back then. So what he did, he realized that the stars were not actually moving in a flat space, but they were going up and down a little bit. While rotating in this Milky Way plane, they were sometimes a little bit above the plane and sometimes a little bit below. And he realized that if you study the up and down motions of the stars, you could find an indication of the amount of matter in the central plane. And Oort was the first one to make a real estimate of the amount of matter and dark matter in the plane of our galaxy.
And now we go to a Swiss astronomer, Zwicky, I believe is the correct way to say it. And absolutely. He's studying not our Milky Way, but the Coma cluster. And herein is the breakthrough, because he uses the redshift of extragalactic nebulas. What is a redshift?
The redshift is a very tiny colorization of light from a distant object. If an object is Well, you know the effect, the Doppler effect that we know from the passing ambulance. When the ambulance is heading towards you, you hear the siren at a little bit higher pitch, and when it moves away from you, the pitch that you receive is a little bit lower. And something similar happens with light. When an object is moving towards you, the color is a tiny little bit bluer than normal, and when it is moving away from you, you perceive the light a little bit more red, and that's the redshift. So the redshift gives you the opportunity of studying the motions towards you or away from you for distant galaxies. And by the time Zwicky did his work, which he did in California actually with the biggest telescopes in the world back then, by that time people knew that the other spiral nebulae were actually galaxies like our own Milky Way. And he studied this huge cluster of galaxies. He studied the motions of the galaxies, and he concluded in this cluster there must be more mass, more gravity than what I would estimate on the basis of what I see. And that was a very first and big important clue to the existence of dark matter.
Yes, he called it Dunkel Materie.
Yeah, in German.
In German, I love this sentence, noch nicht geklärtes Problem. Wonderful. I get it. Fine. It's not clear what's happening.
Not yet cleared up. Yeah.
And
it still isn't.
Does he use the word invisible? I can't see it. There's something there.
He used the term dark matter. Dunkle materie means dark matter. So he was talking about matter that he realized we can see the gravitational effect of something, but we don't see all this matter. We only see the stars and the gas that we use to see with our telescopes, but that's not enough to explain all the gravity. So yes, he was certain that there must be lots of unseen matter there.
I love the modesty of Jan Oort when he says, this is something completely new. I have no idea where we can find it. That dominated the conversation in the 20th century. Is that correct?
It is, because the quote you just mentioned is from an interview I had with Jan Oort for a Dutch astronomy magazine. I think it was back in the late 1980s or early 90s.
My note has 1987 from your book.
Okay, 1987. Thank you. And I was asking him about this problem, and he was very, well, you know, scientists are used to not knowing things. That's the nice thing of science. If you knew everything, you couldn't do any science anymore. So the riddles and the puzzles are the things that they like. And Jan Oort definitely realized that he did not have an answer to this problem. And unfortunately, he died in the late in the last century. And he did not live to see the problem because there still is not a solution to this whole issue.
So these three men early in the 20th century identified what we can't find. Yeah. And we're going to spend the rest of this conversation looking for it. It's a wonderful, wonderful treasure hunt. The book is The Elephant in the Universe, 100-Year Search for Dark Matter. Govert Schilling is the author. We're looking for something that we can't see, we've never found, and we're going to try to imagine how we can certify it exists. We need theories, wonderful, but how do we certify it? Now we come to Jeremiah Ostriker, who, thanks to Govert, I've been led to his book, Heart of Darkness, published just a few years ago. He is an astronomer with firm ideas. And one of those firm ideas is to picture again what we can't see. It's called the halo effect around our galaxy, the Milky Way, around all galaxies. What is that? How should we picture it?
Yeah, it was a strange situation because, as we discussed before, Fritz Zwicky was the one he was the main one who realized there must be a lot of unseen matter in galaxies, but no one paid too much attention back then. And only in the 1960s, the late 1960s, there were those theorists like Jerry Ostriker who started to calculate how a massive galaxy like our own Milky Way galaxy could be stable, because it's all these rotating stars and gas clouds in a flattened disk. And when he did the calculations using the first generation of big computers back then, he realized that a flattened disk of stars cannot stay stable. It can only be stable when there is a big spherical halo around it filled with some kind of matter. So he proposed that our Milky Way and other galaxies also would be surrounded by a big halo of unseen matter, and it fitted very nicely in with his observations by Zwicky and the first pioneering work by Jan Oort and Jacobus Kapteyn, that there must be unseen matter in the universe. So now we had a theoretical reason to believe it too, because without this big halo, this surrounding spherical cloud of dark matter, a galaxy could not even be stable.
It would fly apart. The carousel would just disintegrate. So now we come to the search, or what didn't start out as a search, started out as a project, this without the big computers or the fancy computers we have today, and without the big telescopes we have today, to look for what this possibility meant. And now we come to one of the wonderful deductions made by astronomers in the 20th century. It's called flattening the curve. Introduce us to Kent Ford, because Vera Rubin's no longer with us, and you had a wonderful conversation. Who is Kent Ford?
Yeah, well, let's start with Vera Rubin. She was a wonderful American astronomer, one of the most prominent female astronomers of the past century. And she did pioneering work in the field of dark matter, but she did not do that on her own. She worked with her colleague, Kent Ford. And when I started to research this book, Vera Rubin, she died in late 2016, so I could not talk to her anymore. But Kent Ford was still alive. He is now a 82 or 83-year-old gentleman. And I visited him in his beautiful home in the countryside of West Virginia. And he came up with all these wonderful stories of how Vera and himself worked on this with this big instrument, studying the rotation of distant galaxies. And when we come to the phrase flattening the curve, I chose that as the title for that chapter, because we knew it from the COVID pandemic that we needed to flatten the curve of the pandemic. But here it's actually an astronomical curve, because when you have this rotating galaxy, like our own Milky Way or the Andromeda galaxy, we know that the rotational velocity of stars close to the center is pretty high. But as you get farther and farther from the center, the rotational velocities start to diminish. They get smaller and smaller, and this curve is actually slowing down. It's lowering. But when Vera Rubin and Kent Ford did the actual measurements, they found that the curve is not flattening at all. No, that the curve did not dwindle down at all, but it stayed flat. So the stars on the outer edges of these galaxies are also moving with a high velocity, much higher than you would expect. And that was the first actual proof that dark matter must exist, because without the gravity of this unseen stuff, those stars and those gas clouds would never rotate at that high speed.
The marvel of how Kent Ford and Vera Rubin worked is that they worked with, I picture this, they had plates, right? Photographic plates. And they would get those plates with long exposures on it. They worked on Andromeda, is my note here.
Right.
So our cousin galaxy, that's heading for us, or we're heading for it, whatever. All right. And they work by hand, going blind, counting the rotations? Is that how they did it?
Yeah, it was a lot of handwork back then. This was also late 1960s, early 1970s, and actually during the whole of the 1970s. But back then, a telescope still had to follow the motion of an object in the sky. And these days, that's all automated. But back then, you had to correct it. So during the night, you had to look through the eyepiece and correct the motion of the telescope in a cold and dark dome. And then you had to collect the light from this galaxy and split it out in its different wavelengths with a spectrograph. And normally, to do that, it would cost you many, many hours of exposure on these photographic plates. And the big advancement that Kent Ford had built was a sort of an amplifier. It was an instrument that amplified the light collected. So now the exposure time was not 20 hours anymore, but just a mere 3 or 4 hours. In our mind, that would still be an enormous task to do this night after night, year after year. But back then it was a big advancement.
And now we go to Chile, because one of the joys of reading Govert's book is that we travel with him before the pandemic and after the pandemic. And In Chile, there are some of the biggest telescopes now on the planet Earth. I understand there's lots of attempts into James Webb and Hubble, but you go to the telescopes that are tracking in real time what was done by Rubin and Ford with their long exposures. And all of their tracking has validated that work. Is that correct, Govert?
Absolutely. Ever since this pioneering work in the 1970s, these measurements have been done over and over and over again. And it's not just the rotation of galaxies, it's also the way galaxies are attracted to each other by gravity, how they move around in clusters, building on the work of Fritz Zwicky, how the light from distant objects is bent by the gravity of these galaxies and clusters in an effect known as gravitational lensing, which was already predicted by Albert Einstein. And all these observations together, they point to the existence of huge amounts of dark matter. And yes, it's true. I've been to northern Chile. Well, I lost count, maybe 14 or 15 times. Some of the biggest telescopes in the world are there. It's an absolutely amazing place. And the great thing there is they're actually now constructing a new telescope, which is named after Vera Rubin. It's the Vera Rubin Observatory. And this telescope will study millions of galaxies, study their distribution, study their shapes, study the way they bend the light from remote objects. And it will actually be one of our biggest instruments to map the distribution of dark matter, although we can't see it as it is, but we can measure its effects.
And this has allowed them to map dark matter in space and time, put all of this together. So at this point, we do have a picture. You can go and look at the picture of dark matter. And this works, this follows from Rubin and Ford's work. And just a moment here where we are so far. We haven't found anything. We've found what we're looking for, which is called dark matter, chiefly because it had a poetic presentation 100 years ago. They didn't actually have anything. It was an image. At this point, once they have identified dark matter, at this point, it seems to collide or at least bump up against the thinking of how the universe started, the Big Bang. Is that correct? So dark matter, Big Bang, how do they work together?
Well, that's a complicated story, and that's actually why my book is a pretty thick book. It's over 300 pages, and I try to explain it to the interested layperson.
And Govert, that's where we're going to go, because I'm just setting up the fact that we now have to reintroduce to everyone the theory of the Big Bang and how we know that and how dark matter fits into our thinking about the very beginning. Yeah. And the first 300,000 years, the first several million years. Govert Schilling is the author. The book is The Elephant in the Universe, 100-Year Search for Dark Matter. Govert's going to take us to the Big Bang and why it is that that's important to make part of the search for dark matter. What happened in the first moments? What is it? How can we imagine it, Govert?
It's an extremely complicated topic, but we see now that space is expanding because all the galaxies get farther and farther away from each other. So the empty space between galaxies is expanding. That's something that we have measured over and over again. So if you try to work that back in time, you must realize that in the past, everything, all the matter in the universe was closer together. And if you go back in time, then it must have started in a very dense state and a very hot state. And that's what astronomers call the Big Bang, which is actually the birth of our current universe. Obviously, there are many, many riddles about the Big Bang. We don't know why it started or how it started. We don't know the details, but we are pretty sure it must have happened. But now the problem is that if you start to study the remaining radiation of this hot phase, the cosmic background radiation, this radiation tells you something about the situation back then. And you see that the universe must have been extremely smooth back then. So maybe a little bit tiny differences in density, but in general, very smooth, like a well-stirred soup. Not much clumps and concentrations in it. But if we look at the universe today, only 14 billion years later, it's very clumpy. We have galaxies, we have clusters, we have big dense concentrations, we have empty voids. So somehow, from these smooth beginnings, we must have, the universe must have evolved towards the current clumpy universe. And the only way that astronomers are able to explain that fast clumping is by gravity, by much more gravity than the amount of stars and gas that we see can explain. So again, this is a very important realization that the universe must be governed by dark matter.
I divide everything we have into many different kinds of elements, but beyond that is called baryonic. Baryonic. That's matter and energy, everything we know. And it comes simple to me after I read the chapter again. There's not enough of it. That's the problem.
That's the whole problem, yeah.
Yes. In fact, there's very little of it compared to the size of the universe. And so we're looking for, no longer we're looking for dark matter. We've got a fancy word for it, non-baryonic. That's what we're looking for. And no one's ever found anything non-baryonic before. Is that correct, Govert? I mean, we've just invented this category.
It's a little bit a matter of definition, but in general, we know that everything that we see around us, our bodies, the chair that I'm sitting on, the book that I'm writing, the galaxies in the universe, they are composed of atoms, and we know atoms very well, and atoms is what we call baryonic matter. It's from the Greek word for heavy, because the nuclei of an atom is pretty massive, heavy particles. But now, if there are other particles that are not part of the world that we know, we call it non-baryonic matter. It's just a jargon term to describe something that we actually don't have any idea of. We haven't discovered it so far, but we know that the dark matter in the universe cannot be composed of atoms. In the past, we thought, oh, all this dark matter that we see the gravity of, but that we cannot see with telescopes, they may be dark gas clouds or very burnt out stars or whatever. But no, today we know it can't be made of atoms. And that we know from the theory of the Big Bang and the evolution of the universe. The only way to explain everything we see around is that there must be matter that cannot be composed of the stuff that we know. So now the riddle becomes a little bit more complicated. First, we only had gravity from matter that we couldn't see. And now we also know that this mysterious matter cannot be of the same kind as the matter that we know of.
Govert includes a quote from the Roman poet Lucretius that was very comforting to me at this point in his book. I read it. Desist from thrusting out reasoning from your mind because of its disconcerting novelty. Weigh it rather with a discerning judgment. Then, if it seems to you true, give in. Govert, I give in, Govert, I give in. So we go now to your conversation with Albert Bosma. Bosma, do I say that correctly?
Bosma, yeah.
He is also a cosmologist and also worked at the same time that Ford and Rubin worked about the rotation of galaxies, but many galaxies. He was he at Groningen, the radio astronomy at Groningen?
That's correct, yeah.
Yes, and he and his colleagues worked out 25 or many more galaxies, and they all have the same rotational disks. So what Bosma does is he validates the work that was done earlier without big fancy radio astronomy.
Yeah.
And it's now fixed that everywhere in the universe, there is, we can find something that is non-baryonic everywhere. He writes a paper called The Distribution of Kinematics of Neutral Hydrogen in Spiral Galaxies of Various Morphological Types. Wonderful. I love these titles. Okay. Neutral.
It's an interesting story because Albert Bosma was a student in Groningen University in the Netherlands in the early 1970s. And around that time, there was a big new radio observatory in the northern part of the Netherlands called Westerbork, the Westerbork Radio Observatory. And it's still operational and it's still one of the biggest in the world. But back then it was the absolute novel thing in astronomy. And he worked with this very new radio telescope. And a radio telescope can see beyond the edge of a visible galaxy. Because when we look at Andromeda, we see the stars and the glowing gas clouds. And then we reach the edge of the galaxy. But the galaxy doesn't stop there. Much farther out, there are still clouds of hydrogen gas that do not emit visible light, but they do emit radio waves. And with this radio telescope, Bosma and his colleagues could see much farther from the center of those galaxies. And he did it not only for Andromeda, but for, as you said, for about 25 other galaxies. So he was the real one who put it on the map. And well, I'm a Dutch science journalist, so I know all about this Westerbork work and the work of Albert Bosma. And I thought it might be a good idea to put this prominently in the book, because every now and then I come across other people from other parts of the world who are very much aware of the work of Vera Rubin, but they don't know about this important radio astronomy work. So I try to set the record straight there.
We go now to naming the thing itself that we can't find. Galaxies cannot stabilize without halos. That's fixed. Galaxies are much more massive than we can see, as Govert just indicated. The Big Bang produced weird particles. I love the science of this, weird particles. And the Big Bang is not sufficient for the baryonic matter. There's not enough of it. So now we're searching for what we're going to look for. What is I remember this in the 1980s as the missing matter problem. I think that's the way they talked about it.
Right.
1984, a paper is written, Is Dark Matter Real? The first candidate is neutrinos. What does that satisfy? What doesn't it satisfy?
It's an interesting story, because the neutrino was discovered in the 1950s, and it's a weird particle. It's not part of daily, everyday matter, but we know it very well. It's all around us. It's produced in the sun. It was produced in the Big Bang. But according to standard particle physics theory, the neutrino has no mass at all. It's a massless particle. But, well, we know in science that theories can be wrong. So people started to think, suppose the neutrino does have a tiny little mass. It doesn't need to be very much, because there are so many neutrinos. Maybe the neutrino is our best candidate for the dark matter. And then people realized, no, it can't be, because neutrinos are very, very light, probably massless or almost massless. So they travel at incredible velocities, almost at the speed of light. And when you have particles traveling through each other at the speed of light, it's very hard for them to clump together on a small scale. They would first, in the evolution of the universe, clump together on the biggest scales. So if the neutrinos were the dark matter, we would start with supercluster-sized matter concentrations, which then had to fragment into smaller parts. But from the history of the universe, we know that the first clumps in the universe were actually pretty small. So the non-baryonic weird particles that we're looking for cannot be the neutrinos. They must be more massive. They must not be hot, as astronomers call the fast-moving particles, but they must be cold. They must be slow-moving. And that's where the term cold dark matter came from.
So we're getting closer to what it isn't. We're eliminating possibilities.
Yeah, right.
And when we come back, we're going to eliminate more possibilities, and we're also going to go to CERN, the Large Hadron Collider, that may give us an example of what we're looking for that is invisible. This is a joy. The Elephant in the Universe is the book, 100 Years Search for Dark Matter. Govert Schilling is the author. We know neutrinos don't qualify, although that's a cool idea because it took them a long time to find neutrinos. And they had a theory and they went looking for it, and it paid off. Gravitinos also don't satisfy. And rather than pursue that, I'm going to come to the cosmologist, Jim Peebles. Jim Peebles says, we have something that is cold, that is dark, that is matter, cold, dark matter. However, it has to satisfy a transformation from the smoothness of the beginning of the Big Bang to the clumps we have today.
Right.
That means dark matter has to satisfy something. Well, calling it weird isn't adequate. It has to satisfy something where what does it interact with in that transformation? What do we imagine? Does it have interaction with anything in our standard model?
Well, actually, not much. We know dark matter, or the cold dark matter, as Jim Peebles called it, must be interacting through gravity, because that's how we how we discovered it. We see the gravitational effect. It must have mass. It must have gravity. Otherwise, it doesn't fit in what we're observing. But it doesn't have an electrical charge, so it doesn't interact with light. It doesn't interact with magnetism. It doesn't interact with radiation. It doesn't interact with other charged particles. It does not interact with the strong nuclear force that holds atomic nuclei together. So the only thing that we think might be possible is every now and then a particle might bump into an atomic nucleus and transfer some of its energy to it just by bumping into it. But that's the only thing, and that's a very rare encounter.
And that's the weak nuclear force. That's not the strong nuclear force. This is not, as you say several times, this is losing its elegance. We're wandering into territory where things are getting not symmetrical. But we're going to go to CERN now because there's a search for the particle that they call WIMP. Why did they call it WIMP? Why did they do that?
Yeah, it's also a fun story because particle physicists thought about this possible particle that might fulfill their needs, and it would be weakly interacting, almost no interaction with normal matter, weakly interacting, but it must have a certain mass, so it must be massive, and it is a particle, so it's a weakly interacting massive particle, or a WIMP. Well, scientists and especially physicists and astronomers, they love acronyms, so it was just a joke to call it a WIMP. And then the funny thing is, I don't know if we have time to go into all the details, but there was a competing group of theorists, and they thought that the dark matter might actually consist of very massive objects that are compact and that would be available in the halo of our Milky Way, and they called it massive compact halo objects, and it were the MACHOs.
MACHO, yes, we'll get to
back
MACHO.
then we had the WIMPs and the MACHOs, yeah.
The WIMPs and the MACHOs, but at CERN, that's where they found the Higgs boson. That's where they're doing the best work. It's a science fiction place. I've only ever read about it and seen pictures, but you go there, it feels like a human being is dwarfed by the machinery. Is that right, Govert?
It's incredible because there's an underground tunnel with a circumference of 27 kilometers. It's a couple of 100 meters below the ground on the border of Switzerland and France. And then on certain points in this underground tunnel, there are huge detectors. They are as big as a cathedral and as massive as the Eiffel Tower in Paris. And all these detectors are stuffed with electronics and sensitive equipment, and they register the energy of particles that are colliding with each other at incredibly high speeds. And by this way, you can create new particles out of sheer energy. And it's one way to look for these mysterious dark matter particles, this cold dark matter, this weakly interacting massive particle, the WIMP. Because if it exists, it should also be created in these collisions. So at CERN is a big search going on to see what kind of particles are created in these massive collisions that we are creating. And is there any indication of a WIMP in these collisional products? And so far, unfortunately, we haven't found it.
Right. They call it the lightest supersymmetric particle. Part of this search involves the theory of supersymmetry, which itself is a wonder. What I wanted to make certain I understood is we're no longer looking at the big, yes, into the heavens. We're looking at particle physics for a search. So this is actually a new trail that's opened up. Is that correct, Govert?
Absolutely. It's one of the, if we are looking at the universe, we can see the effects of dark matter on a big scale. We see this in the rotation of the galaxies, in the motions of the galaxies in a cluster, in the gravitational lensing. We can map the dark matter as this new Vera Rubin observatory in Chile will do, but we cannot see the properties of the dark matter particles. We can only see its effects on a large scale, but you cannot get to the nature of the particles. And if you want to do that, you have to do experiments here on the ground. You have to go to CERN to see if you can create dark matter particles, or you have to go to an underground laboratory there are a couple of them around the world, in Japan, in Italy, in the United States, to see if you can see the very rare interactions of dark matter particles with atomic nuclei. So to see the particle in in its detail, we need to do experiments here on the ground.
We also can simulate the universe. Now, this goes from particle physics to a computer, because we're not going to be looking at the heavens. We're not going to be looking at the Hadron Collider. We're going to be imagining. And Govert introduces us to a team, Illustristing, TNG. In other words, they have these lengthy acronyms that are difficult to pronounce, but in any event, they're simulating what the universe would look like if the dark matter clumps. Are they successful?
In a sense, yes, but a computer simulation is just a computer simulation. It's not reality. But what these groups are doing is simulating the evolution of the universe right from very soon after the Big Bang, and they see how the universe would evolve and how the smoothness of the Big Bang is evolving into the clumpiness of the current universe. And you can do that in very different ways, because you can play with the characteristics of your universe. You can put in a little bit more dark matter or a little bit less. You can try to see what happens if neutrinos are the dark matter, or if you use cold dark matter. You can change the properties of the dark matter. And eventually they came upon an evolution that precisely predicts the current evolution of the universe, and it's exceedingly successful in explaining how the universe looks right now. So then you think, well, apparently this computer simulation must be a representation of how the evolution of the real universe went. But still then it's just a computer simulation, and we don't know the properties of this dark matter, and we still haven't found it. But it's very important, because without these computer simulations, we could not know what kind of particle we are trying to find, and what we're actually after.
Does the computer simulation help with this question of how you go from the smoothness to the clumps? Does it give?
That's the most important thing that they're doing. It's actually explaining how the universe evolved in the long run. And well, there's a lot of information going into that, including the background radiation from the Big Bang and the observations in the remote universe, where we look back billions of years in time, and then the information we have from the current universe. All that is worked into these computer simulations, and you try to find out, how did you get from the smooth universe back then to the clumpy universe that we have now? And the only way that can be that they succeed in simulating this evolution is by using this so-called cold dark matter, this WIMP type of particle that is moving slowly, is rather massive, and then everything fits together. So in that sense, they are successful, but still they predict the existence of something that we have not been able to find so far.
The book is The Elephant in the Universe, 100-year search for dark matter. We've not found it. Govert Schilling is the author. The universe doesn't hold together unless we can find something called dark matter, or unless dark matter doesn't exist, then we cannot explain how the universe holds together. It's that puzzling. So Govert has introduced us to the reasoning of what this particle might look like. They call it a WIMP, weakly interacting massive particle, WIMP. However, the searches continue, and we're going to go to one of those searches. But before we go there, Govert surprises in his explication to introduce a chapter about a heretic. The man's name is Milgrom, and he and his colleagues are using Newtonian physics to explain what we observe in the heavens. This is the part that I loved completely, because this is not contrary. This is what about. And what I take is there are some cosmologists who accept the contrariness of it, and some who are annoyed by it. Is that correct, Govert?
Absolutely. This is an interesting story, because Milgrom and his colleagues, they came up with a brilliant idea, because we still haven't found dark matter. And we see it all around us. We see its effects in the motion of galaxies and clusters, in the rotation of galaxies, in the gravitational lensing. But if you start to realize what's actually happening, the only thing we see is the gravitational effect of dark matter. And to explain the gravitational effects that we see, we use our current theory of gravity, which is actually old Newtonian gravity and then superseded by Einstein's general relativity theory. Now, Milgrom asked himself, what if our ideas about gravity are wrong? If we do not have the right theory of gravity, we might draw the wrong conclusions about what we're seeing. We draw the conclusions that there must be dark matter by using our current theories of gravity. But if the theory is not correct, it may be so that dark matter does not exist. And he came up with a modified version of gravity, and he called it a modified Newtonian dynamics, so the MOND theory. And it was sort of a made-up theory to fit the observations, but it was constructed decades ago, and almost half a century ago, and even now people are still not able to really refute it. It's still a possibility that our ideas about gravity are wrong, and if that is true, well, who knows? Astronomers and physicists might be chasing a mirage, and they might be looking for dark matter that does not exist at all.
And Govert gives me to understand there's a generational conflict in cosmology right now. The senior cosmologists, my aging group, Jeremiah Ostriker is one of them, regard this heresy as unacceptable, a waste of time. I think Ostriker's wonderful quote is, we might as well write papers about why humans can't fly. Okay, fine. But you speak to Stacy McCaw, I believe is the way you say it. The fact that MOND works at all is a problem for dark matter. So in theory, they've come up with a theory that suggests that there might be something to examine here. And
yeah, and their main success, the main success of this MOND group, the Milgrom and McGogh and their colleagues, the main success is in these rotational properties of galaxies, because the galaxies are rotating in a weird way. The outer parts are moving too fast. That's something that Vera Rubin found, that Albert Bosma found. We see that in each and every galaxy. So there must be something happening there. The traditional way of explaining this is by having a lot of dark matter distributed in this galaxy in a certain way, so we can explain all these velocities. But the MOND theory explains it without any assumptions. It just have this slightly modified version of our gravitational theories, and it can explain all the rotational curves of galaxies perfectly. And that's a big success for MOND. And that's a bit of a worry for the traditional physicists, because even if there is dark matter, they have to explain why the dark matter behaves in such a way that it actually fits this theory. It's a little bit an inexplainable thing.
We're back to astronomy. Let's go look for dark matter. Even if we can't find it in particle physics, we can see it. And here again, we go to one of the wonders of the 20th century, gravitational lensing. My understanding is Einstein's telescope, that gravity affects light, or the energy that comes to us from far away. So that allows you to see things that otherwise might not be visible, but it's distorted as it goes around the edge of a galaxy or a star. So where do they think we can see cold dark matter using gravitational lensing?
Well, actually, it's not so much that you can see what kind of dark matter we're talking about, but it's possible to map the distribution of dark matter by using gravitational lensing. Because if a very distant galaxy is sending its light toward us, this light is being slightly bent and curved by the gravity of all the intervening mass. And that's not just visible galaxies and clusters, but also the distribution of this mysterious dark matter in the universe. And if you look at millions of galaxies, and that's something the Vera Rubin Observatory is going to do, but also a couple of future space observatories, if you do this and you study the statistical properties of their shapes and their distribution in space, you can, by mapping this effect of gravitational lensing, you can also make a map of the distribution of dark matter, not only in space, but also in time, because you can do it for very distant galaxies where we look back billions of years in time. So the eventual hope is that we can create a 3D map of the distribution of dark matter in our universe. And that's something that gravitational lensing is very, very good at. And it's a way to another way to see the effects of dark matter in space.
The bullet cluster. This was a treat to imagine, well, if there is dark matter and one cluster, one nebula is running into another, what happens to the dark matter that surrounds them? Does it bump up against other dark matter? Does it distribute in a way that we can't expect? I was ready to be told again that this contradicts everything we have, but I couldn't tell from the images. Can we see where the dark matter bumped into other dark matter, or is it?
Yeah, this is maybe a hard part of the book. It's not a simple topic, but this bullet cluster is actually two clusters of galaxies merging, passing to each other. Now the galaxies themselves are far away from each other, so they can actually pass to each other pretty undisturbed. The gas in between the galaxies is everywhere, so the gas atoms, they start to interact. But that's normal matter. These are charged particles. They feel the electrical force, magnetic force. So the gas clumps up together in between the two colliding clusters. But now if you talk about the dark matter, this is also non-interacting stuff. So it moves through each other just like the stars would do. And by mapping the gravitational lens effect of this bullet cluster, you may try to see where most of the mass ended up. And the first indications was that it is actually confirmed the existence of dark matter, because it looked like the two biggest mass concentrations were still surrounding the two individual clusters, which could only be explained if the dark matter was still within these clusters. So it looked like the bullet cluster observations were refuting the MOND theory. But, well, as it goes in science, those people with the alternative theory, they don't give up too early. So they are still working very hard to explain it with their own modified Newtonian dynamics theory.
Right, still possible with neutrinos. You went to the Very Large Telescope for this experiment. They were tracking the bullet cluster, and you believe that when the extra large telescope, what is it, the extremely large telescope?
Extremely large telescope, yeah.
Will that be a better tool to witness dark matter?
Yeah, because this is a European project, and they're building the biggest telescope in human history with a primary mirror almost 40 meters in diameter. So it's a huge construction, and it will be finished in a couple of years. And today we all think, well, if you want to study distant galaxies, you need the James Webb Space Telescope. And that's a wonderful instrument for a lot of science, because it's in outer space and looks in the infrared. But its mirror is only 6.5 meters. We couldn't launch something much bigger. So here on the ground, we're building something with a mirror 40 meters in diameter. And that will be very important to study extremely faint objects. And it will be a very important telescope to study structures like the bullet cluster, and to study the gravitational lensing effects of certain objects that we hope we can be able to confirm or to refute the popular dark matter theories.
We're going in search of dark matter now, and we're going to try something that Govert has already mentioned. This is the wit of cosmologists. We're going to go in pursuit of the MACHO. The book is The Elephant in the Universe, 100-Year Search for Dark Matter. Govert Schilling is the author, but the search continues. And one of the ways to search is, well, if it's not small, what if it's massive? What if it's massive, complex halo object, MACHO? What if gravitational lensing can give us a result that we haven't been able to find because we were looking for something small? As far as I can see right now, there are teams who exhausted themselves in the late 20th century. Has MACHO now been retired, or?
Yeah, absolutely. Absolutely. But it's a very nice story, because it's a very neat story to explain how science works. Back in the 1980s, everybody thought dark matter must be this non-baryonic, cold dark matter, weakly interacting massive particle. And that's where the physicists started to work on. And they had all these theories, and they tried to look for it. But then in science, you always have to think, yes, but what if? What if dark matter is actually something else? Or what if dark matter might be these WIMP particles, but there might be other types of dark matter too. We can't exclude it. So we need to look for other types of dark matter too. You need to be sure that some other explanation cannot be the whole or part of the truth. So what they started to do was looking through this gravitational lensing at the existence of dark massive objects in the outer parts of galaxies. And the only way you can do that is by looking at the way such a dark, invisible object would bend and amplify the light of an individual star. And it's a very rare event. So if you want to be successful in that, you have to study hundreds of millions of stars. And you have to use electronic detectors and big telescopes and computer algorithms to study all these measurement data. And that's what two teams in the 1990s started to do. And they spent a lot of effort in it. It was a big race. And in the end, they had to admit, well, we did not find these massive compact halo objects. Probably they don't exist. And it's not that their search had been for nothing, because it was very important, because they could exclude this remote possibility. And that's the way science should be done. You shouldn't be only following the mainstream. You always have to check, what if this is true also? What if the truth might be hidden somewhere else? And you have to check that, all of that. And if you don't find it, it's still a very good and important result. And that was the MACHO story.
Just in case you thought this was getting too simple, we now take you to dark energy. Govert, this is wonderful. The universe is accelerating. It's expanding, and it's accelerating at some point. It's accelerated. And in searching for dark matter, the cosmologists find dark energy, which when I got to this chapter, I thought, oh, great, I haven't found dark matter. Now I've got to go look for dark energy. But as I understand it, they reason to this because the expansion was slower in the past. They've witnessed that. Is that correct, Govert? They can document it.
That's true. In 1998, there was this revolutionary breakthrough in cosmology that two competing teams with different techniques and different instruments, they arrived at the same unexpected result. And that was that the expansion of the universe is not slowing down with time, as everybody had expected, because gravity would slow the expansion down. No, the expansion is speeding up. So we live in an accelerating universe. And the only way to explain that is to assume that there is some mysterious mysterious vacuum energy in empty space. And that's what we call dark energy. But we gave it a name, which doesn't mean that we know what it is. So today's cosmology is extremely successful in explaining everything in the universe and how it came from the smooth universe back then to the clumpy, accelerating universe that we witness now. But the only way they can explain it is by assuming there are huge amounts of mysterious dark energy and also very large amounts of mysterious dark matter. And we don't know what dark energy is. We don't know what dark matter is. So most of the universe that we can explain is still a big question mark. And that's a little bit, well, uncomforting, I should say.
Yes, but you have a chapter, The Pie in the Sky. We're going to picture now what, with dark energy and dark matter and baryonic universe, that's us talking, what we believe is everything now. Us is 4.9% of everything, which isn't quite, it used to be 5%. We got demoted. And dark matter is 26.6% of everything. And that means dark energy wins. Dark energy, 68.5% is my note here. Dark energy is the explanation for dark matter, but we still don't know what it is.
Dark energy is the most important factor in our current universe. I have here this empty water bottle, and it's fun to realize that if this is half a liter, and I don't know if everybody is watching this, but otherwise, if you're just listening, you can imagine that only the bottom part of it, just a tiny bit of water on the bottom, is the matter that we know of in the universe. That's the baryonic matter. That's atoms and molecules. And then about 1/4 of the bottle is mysterious dark matter. But the majority, 3/4 of this empty bottle, is dark energy. We don't know what it is, but it's governing the evolution of the universe right now.
And in governing the universe, we've now come this far because we started to look for something that wasn't there. That's how we got to this place, searching for dark matter. But we need to introduce one more thing before we turn the page to the experiments that are ongoing. Einstein came up with the cosmological constant, which is signified by the Greek letter lambda. And later on, he said it was the worst mistake he ever made. We need the cosmological constant. Is that correct?
That's right, because the cosmological constant that Einstein once introduced was in effect an accelerating force in empty space. And back then he thought maybe I should never have introduced it because later cosmological observations they seem to indicate that it was not necessary. But now we are discovering that the universe is accelerating, that the expansion is speeding up, and the dark energy might be Einstein's cosmological constant. Right. So in a sense, it was foreseen by this genius Albert Einstein a century ago.
The book is Govert Schilling's Elephant in the Universe, 100 Years Search for Dark Matter. 100 years from now, 200 years from now, they'll know much more about where we were right and where we were wrong. Govert is giving you the best right now that exists in the universe about the search for the universe that we're searching for. And we come now to the cosmic microwave background and what that tells us about dark matter and about dark energy and how we need it. The cosmic microwave background, as everybody knows, is something that was found in the late 20th century by looking at the sky and saying, what is this buzz, like radio fuzz in the backgrounds? That's left over from the very beginning. That tells us that the universe was, well, the way I think of it is the universe was flat when it started. Is that right, Govert? It wasn't, it didn't have dimensions. It was flat.
Yeah, it was in a sense flat in the sense that it was very smooth, no large-scale curvature of space. So the main thing of this cosmic microwave background is that it's the last. It's actually the only signal that we have from very soon after the Big Bang, only a few 100,000 years. So it's the oldest light in the universe that we can study. And when we study this microwave background with big radio telescopes here on the ground and with satellites in space, it gives us some information about the structure of the universe back then. And you remember that we talked about Jim Peebles, who was wondering about how could the early smooth universe evolve into the clumpy universe right now. Well, the microwave background shows us that the early universe was almost smooth, but not completely smooth, because we see tiny fluctuations in temperature and in density. And the pattern of this distribution of these fluctuations in the background radiation, that is a very important clue to the ingredients of the universe. With different mix of ingredients, these clumpiness of the background radiation would be different. So now we look at the microwave background, and astronomers can use this information to predict what the current ingredients of the universe are. And that's this dark energy, a mystery, dark matter, also a mystery, and the baryonic matter, the atoms and the molecules that we know of. And they come up with exactly the same recipe that we discussed before. It's actually from the microwave background that we know this percentages so accurately. And the funny thing here is that this study of the cosmic microwave background is pretty new. The latest observations were only published in 2018, and they give us a clear indication that there must be dark energy, there must be dark matter, and I find this interesting, even if we did not have all the information from Vera Rubin and Albert Bosma and Fritz Zwicky and the gravitational effects, if we did not have all of that, and we just had the microwave background from the Big Bang, our conclusions would still be the same. We cannot do without dark matter. So the microwave background, the radiation, the echo of the Big Bang, if you would like to call it that way, is very important. And it's a confirmation of our ideas about dark matter.
At this point in the telling, Govert admits this is circumstantial evidence. Yes, okay, fine, you got us. So let's go to Gran Sasso. This is Italy, way underground, that apparently you find this by taking a road through a tunnel and you turn left and you turn right. I don't know, I got lost. It worried me how much mountain was above you. But here we have an experiment to find the thing itself using xenon. Very dedicated people. There are more than one in Italy. They're around the world. They've entertained Ontario, South Dakota, New Mexico. Some are underway. They're looking for what the WIMP, the weak interacting massive particle, is going to interact with. And they're waiting. What's the experiment look like? Take us into the tunnel and the cave.
Yeah, it's an incredible experience because this cave deep underground is huge. Big trucks can drive in and out of it to carry equipment. And there are all kind of big science fiction-like installations. And there's a sort of a dusky atmosphere, and it's cold, and it's like an underground mysterious place that you are not allowed to go into. It's really out of a horror science fiction movie. But the experiment itself is actually a very big tank of water, and inside the water is a vat with liquid helium. And the idea of the experiment is that if dark matter is so abundant in the universe, it must also be around us. And we cannot measure it because it doesn't interact with normal matter. But every now and then, very rare, it might collide, one dark matter particle might collide with a big atomic nucleus. And if you see the effects of such a collision, you might be on the track of dark matter. And then obviously you have to shield your experiment from all other kinds of interactions, from normal particles from space, particles from natural radioactivity. So that's why the experiment is so incredibly high tech and has to be deep underground. But well, so far these experiments also have not given us the solution to the riddle. And that starts to become a little bit worrying because we have newer and bigger xenon experiments, both in the United States, in South Dakota, and in Italy, in Europe, and in Japan, and in China. And all these experiments are still giving up null results. They do not find evidence for the existence of dark matter. And now people start to scratch their heads. What if we will not find it? What do we have to conclude? What is the solution to our problem? That's already a century old.
Yes, you call them the xenon wars, but let's go to an experiment that isn't the xenon war. It's called DAMA, D-A-M-A, and it's using high purity crystals of sodium iodide. Now, they've come up with a result, but I don't know whether it's a result that proves anything, but it is interesting. Apparently there's seasonal change. There's a seasonal pattern. Please help me understand.
Yeah, well, if there is a sea of dark matter around us in this halo of the Milky Way, then our sun must be moving through this halo. And that means that, and then the Earth is circling around the sun. So every now and then our Earth is moving in the same direction as the sun moves through the halo, and the other half a year later, it's moving in the opposite direction. So one half of the year, you should see a little bit more interactions of dark matter particles, and the other half of the year, a little bit less. And this DAMA experiment, which is the D-A-M-A, actually stands for dark matter. The DAMA experiment claims that they see this seasonal effect. And the thing is that if they are correct, it would be a big breakthrough because we would have found dark matter, because apparently they see this effect that you expect from these particles. But no other experiment sees the same thing. They don't even see the particles themselves. They have tried to replicate the experiment, and they don't see a seasonal effect too. And the DAMA experiment is the only one who has this claim. So other scientists are very busy trying to explain their conclusions in a different way. Maybe they have some bug in their analysis, or they draw the wrong conclusions. It's a big unsolved mystery there.
We go to another experiment underway at the International Space Station. This is a search for messages from space, is what Govert calls it. I think they're looking for something like antimatter, but I'm not sure. Samuel Ting is the Nobel laureate who was very generous with you, very generous. And what did you learn from his experiment at the ISS?
Well, it's still running. It's an interesting experiment because it's actually a particle detector flying in space. It's not as big as the detectors in CERN because you couldn't launch that, but it's pretty big. It's on the outside of the space station, and it detects particles that are flying through interstellar space, and they are all around us, and they are hydrogen nuclei, and there are electrons, the particles that we know of, but they also see particles of antimatter. And there's one theory that if there is dark matter in the universe, then every now and then two dark matter particles could collide with each other, and they produce maybe antimatter in the process. And if you see too much antimatter in an experiment like the AMS on board of the International Space Station, that's the experiment we were talking about, if there's too much of this antimatter, it might be coming from dark matter in the center of our Milky Way. And right now, they are not yet sure that they are seeing this too high abundance, but maybe when they collect more evidence over the next 5 years, we hope the space station will be running at least until 2028. So there's still 5 or 6 years to go. They may have collected enough data to conclude that their antimatter measurements are pointing to the existence of dark matter collisions in the center of the Milky Way.
The book is The Elephant in the Universe, 100-Year Search for Dark Matter. Govert Schilling is the author. And we come to, an exception. They found a galaxy without cold, dark matter. They found several of them, in fact. And that worries everybody. Or the quote, DF44, that's the name of the galaxy. They call it the Dragonfly Galaxy, is a problem for everybody. Is it a problem for MOND too?
It is a problem for MOND too, because MOND is this alternative theory that tries to explain dark matter not by introducing a new particle, but by assuming that our theory of gravity is wrong. Now, if MOND is correct, then we should see the effects of MOND in each and every galaxy, because they don't assume that there is dark matter. They just assume there are stars and gas clouds with a different gravity than we are used to think of. So according to MOND, each and every galaxy should show these effects of their alternative gravitational theory. And if you see a galaxy without the gravitational effects that we attribute to dark matter, then it cannot be explained by MOND too. So there is this strange galaxy, they found a couple of these dwarf galaxies that seem to be devoid of dark matter, and no one has a good explanation for it. And so it's another way science works. You can have theories, you can have experiments, you can make conclusions and think that you will almost solve the problem. But nature always has the last word. And if nature comes up with a galaxy with no dark matter, you need to be able to explain that. And you need to go back to the drawing board and start over your calculations again.
I said earlier, my favorite chapter was MOND. I forgot my favorite chapter was chapter 24, The Dark Crisis. This is wonderful. All right, put your thinking caps on, because we're about to imagine why it is we can't find dark matter, why we can't find WIMPs. There are a couple of versions here. There are more to come, but these are great. Black holes. Dark matter is black holes, but not ordinary run-of-the-mill black holes. Primordial black holes. What is a primordial black hole? What's the theory?
Well, we hardly know what regular black holes are, but we know that a massive star can end up as a black hole, or in the course of galaxies, there are massive black holes, and those are the black holes that we know of. And they evolved from normal matter in the course of the evolution of the universe. But primordial black holes, they were born during the Big Bang, or maybe even at the time of the Big Bang, because matter back then was so compact and so dense that maybe if there were big fluctuations in this primordial soup, there could be small black holes that are concentrations of matter that started to collide onto each other. And these primordial black holes might be much less massive than the normal black holes that we know of, and it might be all around us. And it could be an explanation for dark matter. So people started to search for it, but so far it doesn't look good because we have excluded many types of primordial black holes. We know it can't be the very lightest ones, it can't be the most massive ones. So there's only a tiny mass range that is left that might be an explanation. And I'm not so sure that that could be the solution to the problem of dark matter.
You speak with Catherine Zurich at Caltech, and she's wonderful about this, that the physicists like beauty, the beauty of calculations and formulas, but that nature is not about beauty. That's what physics wants. That's what nature doesn't deliver. So a primordial black hole as small as a nucleus that weighs as much as a sun or several suns. That's one idea. This one also, fuzzy dark matter, something very, very weak, very, very weak, 10 to the minus 22 electric volts. That's almost non-existent, isn't it? Fuzzy dark matter, decaying dark matter. Oh, here's one I like, that the reason we're accelerating is that the dark matter there's less dark matter and there's more dark energy. Is that how it works?
Yeah, I have to explain that all these weird theories that I describe in this particular chapter, it's all very speculative because theorists it's their job to come up with new ideas and they have to think of everything. But for all the things that you mentioned, including the fuzzy dark matter and the decaying dark matter and what have you, there's actually no evidence, no physical evidence, no observational evidence that it might be true. So it's sort of a, yeah, it could be an example of despair among the physicists that they have to come up with all these weird theories to explain the riddle because we can't find the particles that we think they must be existent out there. So it must be something else, and they come up with everything they can think of. But you really should realize that it's all just theory and just speculation. And for all these possible alternatives, there's no physical evidence so far at all.
I enjoy the theories, though, because they take me beyond what I can picture. I mentioned, let's go to the Ferlin brothers, Eric and Herman. This is wonderful because they make it possible to imagine that dark matter, dark energy might be emergent gravity from the beginning. That is, I've tried to picture this, Gunnar. Are you able to picture it, what they're talking about, the gravity coming out of the beginning?
It's so hard, John. I'm not a professional scientist myself. I don't have the full theoretical background to understand all the theoretical details of this. And I talked to Erik Verlinde, who he's a pretty famous and absolutely brilliant theoretical physicist at the University of Amsterdam. And he came up with this theory of emergent gravity, that gravity is not something that is existing on its own, but it's emerging from a lower level of existence. He compares it a little bit to temperature. We all know that temperature exists, but when you look at the details, at the tiny details, an atom doesn't have a particular temperature. And temperature is something that is emerging from the motion and the collisions and the vibrations of atoms and molecules. And maybe gravity is something like that space-time, empty space-time and gravity is emerging from a lower, deeper level of reality. Now, if that is true, and I have to admit, I don't understand all the theoretical details, but if that is true, then dark matter maybe does not exist, and dark energy might be something that more has to do with the horizon of our cosmological observations than with empty space itself.
I thought it was a clue to Verlinde's thinking that his brother Herman is a string theorist, because I've tried string theory, and that's equally challenging to picture.
Yeah.
Now, the payoff of your book for me was this proposition. What if the modified Newtonian physics is working in concert with the lambda cold dark matter. They're both correct. Is that fresh thinking? Did you just discover this?
It is a fresh way of looking at those things. And in a sense, some of the alternative theories that you are describing may go toward that goal. The fuzzy dark matter that we mentioned is something that is not a real part. It's a particle so low in mass that it's hard to explain, but its corresponding wavelength is extremely low, so it starts to act more like a field instead of like a particle. And then when you have something like a field, it is something like the MOND field, which is also a gravitational field. And Erik Verlinde's theory has a lot of comparisons in its results with the MOND theory. So a number of theorists are thinking about new lines that may end up more or less in the same way as this modified Newtonian dynamics. And maybe the MOND people like Mordehai, Milgrom, and Stacy McGough and their colleagues, maybe they are onto something, but they just didn't have the right way of describing it. And other theorists are now finding a proper way to give the right description, but it's all still very much unexplored. Let's call it that.
The search continues. Particle physics, deep in mines, the big telescopes in Chile, the ISS, and theoretical physics still turning over and over theories to see a new way to explain the search for dark matter. The book is here now, however. The Elephant in the Universe, 100-Year Search for Dark Matter. Govert Schilling is the author. This is CBS Eye on the World. I'm John Batchelor.